right, so today we're going to look at 2.8, function operations and composition. Operations means that you're going to add, subtract, multiply, and divide. The composition functions are the ones where you do like f of g of x, and you're taking one function and putting it into the other. Not only are we going to do that, though, we're also going to look at the domain of those functions, and that might be a new concept. It varies depending on what you're doing. So let's go take a look. Now, when we're dealing with domain, there's kind of three scenarios that we typically deal with. So in a perfect world, there are no restrictions and functions can, have a domain of negative infinity to infinity. Perfect scenario. The times where that doesn't play out as nice, for us anyway, just a couple common ones, are when you have a fraction and you don't want to end up with a 0 in your denominator. That presents a problem. Or if you have a radical and you don't want to end up with a negative number because then it goes imaginary. So looking at those, just a recap, we've done the domain thing before. So when you look at this, you should see on this 1a that you do not want the denominator to be 0. Now, sometimes you're just going to be able to do this in your head, and this one probably so. If it's a little fancier, you do something like this and say, all right, so x cannot equal 3. That's going to be the domain. So when I go find it, I want to make sure that does not happen. If you do that in interval notation, it's a little tedious. If you want everything except 3, then it's negative infinity up to 3 with a parenthesis, meaning it can't be the 3, in union with, and then you do it from 3 to infinity. And all of that includes everything except for the 3. This first method is kind of nice, but sometimes we're required to write it in interval notation. Okay, let's look at B. This one, we have the radical. And so what you don't want to have happen is you do not want to have that be a negative number. So what we can do, again, you might be able to do it in your head. If not, you set up a little inequality. X minus 3 needs to be greater than or equal to, it's okay for it to be a 0, greater than or equal to 0. Add the 3, so you're saying X has to be greater than or equal to 0. If you can, I'm sorry, not 0. Greater than or equal to 3. If you think of that on a number line, and you got 3 right here, you want everything greater than that. So putting that into interval notation is actually pretty quick and our preferred method. It can be anything from 3 to infinity. Now, in this case, it can actually equal 3 because you can take the square root of 0. Cannot be infinity. Okay, let's fancy this up a little bit, give you some more that maybe it's not quite as obvious to see how to do that in your head. So looking at this first one, I don't see a fraction. I don't see a square root or any kind of root. So your domain on this is just going to be negative infinity to infinity. No issues. All right, this next one, I see a fraction. I do not want the denominator to be 0. And this is a little trickier and takes us back to a previous chapter when what I really want to be careful of here is that this quadratic, whatever that is, it needs to stay greater than or equal. I'm sorry, that's an inequality. So I take back what I said. Really, this is just a cannot equal 0, like that. All right, so now when you see the quadratic, you need to factor that. And then that's going to be a 3 and a 1, a minus 3 plus 1. So when you look at it as it cannot equal 0, you sort of are setting it up like it was equal to 0. So you would do this thing right here where that can't equal 0 and this can't equal 0. So ultimately, your domain, x cannot be negative 1 or 3. We could put that in interval notation. It would have a couple chunks of well, heck, let's do it. So it'd be negative infinity, because I think on your assignment, that's how they're going to want you to enter it. So negative infinity to negative 1, can't be negative 1, in union with negative 1 to 3, can't be 3, in union with 3 to infinity. So you end up with several pieces of that. Every time you include another restriction, it's going to do that to you. All right, next one is C. We have a square root here. We do not want this to be negative. So I take the 3x plus 12 and I say, all right, got to keep that greater than, can equal 0. All right, subtract the 12, divide by the 3. Boy, I'm struggling today. Sorry. Negative 12, divide by 3, and you get this right here. X has to be bigger than negative 4. If you wanted to write that in interval notation, bigger than negative 4 means like this, but it can equal the negative 4, so I do the bracket. All right, last one. I'm throwing them together. I have a fraction and a radical. What do you think is going to change on that domain compared to just doing the regular radical? All right. What changes is that it can no longer equal 0. So when I set this up and say 14 minus 2x, and last time I said is greater than or equal to 0, now it's just greater than 0 because I cannot let it be 0 because it happens to be in the denominator. All right, in this scenario, I would probably add the 2x to the other side, divide by 2. But it is a little bit weird because now my x is on the other side. If you're one of those people like me that kind of likes it to be on the left, you switch it around, but make sure it's still pointing at your x. So x has to be less than 7. In interval notation, that would mean negative infinity to 7 with a parenthesis on this one. Okay, so now we're going to look at combining the functions. We did kind of a recap of domain because that's going to come into play later. To combine functions just using operations, adding, subtracting, multiplying, dividing, there's nothing fancy. If this is the notation that you see with this f plus g of x, really all that means is that you're going to take your f of x function, your f function, and you're going to add it to your g function. But this is the notation of how that's written, where you combine it together. Same thing here. I guess I'll take a moment and go ahead and write these all in. You're just going to take those two functions. Now, this is kind of a weird notation. That actually means multiplication. We don't put the dot there. We just write f times g with nothing because they're just both variables. So it works. So you're going to take your f function and you're going to multiply it by your g function. Now, of course, after you do any of those operations, you're looking to simplify it and combine like terms. And this last one, you're going to take f of x and you're going to divide it by g of x. And right there is where we start to have domain issues, because now you want to make sure that your g function doesn't equal 0. All right, let's look at some. Just doing the operations, not worried about the domain right now. But notice what I've done here. Instead of just writing f plus g of x, I wrote f plus g of 2. So what that means, and you can do this a couple ways, you can take the f function and add it to the g function and then plug 2 in. So I would take this plus this and plug the 2 in. On this one, I'm going to show you both ways, and then from here you get to choose. So if I were to add those functions together, I'm really just looking for combining any like terms I can. I have an x squared, I have a 3x, and then they both have a constant, so I'll go ahead and add those together. So that's the combination of them. Now, if I want to do the f plus g of 2, it means plug 2 in for x. So you get 2 squared plus 3 times 2 plus 6. So that's 4 plus 6. That's 10 plus another 6. We'd get 16. All right. Now, the other way you can do it, and I'm going to tell you that if you had like an f plus g of 2, f plus g of 7, f plus g of negative 3, f plus g of 15, and you had the same operation happening over and over, and all you were doing was changing your x value, this is definitely the way you'd want to do it, because you'd want to condense it all. Now, this one isn't real tricky. It can be trickier than this, but the other thing you could do is just go ahead and just do this. Plug 2 into the f, plug 2 into the g, and then add your two answers together. All right, remember, we're looking for a 16 here. So I'm just going to do this off to the side, and then, so if I were to plug 2 into the f function right here, that'd be 2 squared, so that'd be 4 plus 1. So that'd be a 5. So what I'm doing is f of 2, oops, f of 2 is equal to 5. G of 2 would equal, let's go look what would happen there. When I put a 2 here, that'd be a 6 plus 5. 6 plus 5 is 11. And then if I try to add f of 2 plus g of 2, you can see right there I'm going to get 16. So either way you want to do it, doesn't matter to me. All right, so on this next one, we're doing subtraction. And for no particular reason, I'm going to do our second method. So I'm going to do f of negative 3. All right, so f of negative 3, putting a negative 3 squared, that's a 9 plus 1. Putting it in right here, 9 plus 1. So that's going to equal 10. Now let's do g of negative 3. Put in a negative 3 here. I have negative 9 plus 5. That's negative 4. So g of negative 3 is negative 4. And if I'm going to subtract, so now I have 10 minus negative 4. So your answer should be 14 on that. I'm trying to show a little bit of work here. If you're able to do that mentally, that's okay. You don't have to show work on some of these. Okay, next one, f times g of 5. Okay, this is one I probably would definitely want to do just individually and then multiply, because otherwise I'm stuck having to take f times g, the functions, and I'm going to have to FOIL them and then plug it in. So I'm not going to mess with taking the time to FOIL. I'm just going to take the 5 and plug it in here. So that's 25 plus 1. So that's going to be a 26. And I'm going to have to multiply that by putting 5 into the g function. So that's 15 plus 5. That's 20. And 26 times 20 is 50 or 520. Okay, I didn't grab my calculator. I'm going to do some mental math here today. So if I goof up, forgive me. All right, so next one, f divided by g of 0. Okay, so taking my f function, and this time I'm going to write it out. I'm going to have an x squared plus 1 divided by 3x plus 5. And now I'm supposed to plug 0 into this function. So let's give that a shot. If I plug, oops, hang on. If I plug 0 in right here, I'd have 0 squared plus 1. So that's going to get you a 1 over, plug 0 into the second one. That's going to be 0 plus 5. So then your answer is just 1/5. Now, I would be a little bit nervous if my denominator ended up a 0 there, but it didn't, so no worries. Now, the thing that sometimes messes students up is the trying to do these kinds of functions with a graph. And so, or maybe with a table even. So let's go through some examples where you're doing that. It's really not that hard. I'm going to do f plus g of 4. So that means I'm going to plug 4 into the f function and see what I get. And I'm going to plug 4 into the g function and see what I get. Now, this is sort of a combined table. You have to think of it. Here's a table of the f of x, and then ignore this and think of another table with the x and the g of x. So if we were to plug 4 in for x, that happens right here. So plugging 4 into the f function gets you a 9. Plugging 4 into the g function gets you a 2. So ultimately what you're going to be doing is you're going to be taking 9 plus 2. Adding, because that's what they're telling you to do right here. Final answer, 11. Okay, now let's look at our graph. Let's try that. So they want us to take f times g of 1. So I'm kind of doing what I did before, but with a graph. I'm going to plug 1 into the f function, plug 1 into the g function, and then multiply those two together. So when I plug 1 into the f function here, that just means x is 1. If I go over 1, look at where my graph lands. It lands right here. So f of 1 is really 3, because that's your y value there. That's what you get back. So that'd be a 3. And I'm going to multiply that by, let's do it again, where you put 1 into your g function. Now your g function is here. So when x is 1, it looks like the y value is 1. So then you're going to take g of 1 is just 1. So when you multiply, you just get 3. Okay, why don't you pause the video for a second and see if you can do the next one on your own. Okay, hopefully when you plugged 0 in for f, you got a 1. Plugged 0 in for g, you got a 0, and uh-oh, we have an issue. Cannot have 0 in your denominator, so this would be considered undefined. Okay, so let's take a look at doing the domain, because that's really where the new stuff is and a little bit tricky stuff is. So when you're doing the domain of these combined functions, you actually have to find the domain of each individual thing. You have to start off and you got to look at what's the domain on f. Then you got to look and say, what's the domain of g? And I'm looking at each individual. And in all honesty, I'm going to add something else. And then you're going to look at the domain of the result. Depending on are you adding them, subtracting, multiplying, dividing, to look at the domain of the result. And you have to look at the restrictions that happen in all three of those areas. And you combine any restrictions at all that happen, and that becomes the domain of the overall combined function. So you kind of have three things you have to look at. Now, it says one additional restriction here, but that you're going to catch that. It says the denominator of the result from division cannot equal 0. So yeah, if my result ends up with a fraction and I have a 0 in the denominator, I'm going to have that restriction as part of my 3 that I'm looking at. Now in these, I'm going to do a kind of a variety of different types of functions, different things that can happen to you. We are looking for the f minus g of x. I'm not putting in a number this time. So I'm really just doing the combining the two functions. So what this means is I have to take this function and I have to subtract that function. Now I'm going to go ahead and write what that would look like. That would be 2x plus 1, but you would be subtracting this entire function, which means you've got to distribute that negative through to each term. All right, so then I'm going to look for any like terms that I would have, plus I'm going to put it in decreasing order of the power. So I'm going to start with a negative x squared, and then you'll see that you have a positive 2x, and you're going to end up with a negative 2x. Those are going to cancel. Okay, that's kind of cool. All right, now let's work on the constant. I have a positive 1, and when I distribute this through, it's going to be another positive 1. So then I'm going to have a plus 2. So that's what f minus g of x is equal. And if I had really good notation, I would be doing this in the front of it. F minus g of x is equal to this. Now let's talk about the domain, because that's really what we're doing differently here. What is your domain on f? Right here. All right, it's a polynomial function, linear actually, and it is fine. It's not a fraction, not a radical. There's no restrictions. Same deal with g of x, no restrictions. So the domain for f would be anything you want. The domain for g would be anything you want, which means the domain for the combined function is anything you want. And then just as a quickie, don't forget, if I ask you to find one and I stick a number here, that just means plug -2 in. Now, earlier I was plugging it into f and then into g and then subtracting, but I've already taken the time to find that combined function, so I'm just going to plug it in once. I'm going to put -2 right here. Order of operations says I have to square it first, so now it's positive 4, but then I make it negative. So -4 plus 2, -2. All right, so got some new functions, got some new operations, a little bit fancier operations. So on this first example, I'm going to be taking f times g of x. So f times g of x just means that I have to multiply those two functions together. So it's going to look like x squared times x minus 3, but cleaning it up. So distribute through, and you have this function here. Now, let's look at them individually. F of x is just a nice, easy quadratic, no restrictions. G of x, same deal, no restrictions. The resulting function, when I look at it, would be then no restrictions. So that is your overall domain, the negative infinity to infinity. Got it. That's a lot of negative infinities to infinity. But the whole key is that you got to look at the individuals first. All right, still no issues. Let's do one that's going to have some issues. All right, when I find f over or f divided by g, or here, I'm going to write it out here. F divided by g is simply going to be x squared over x minus 3. Now, sometimes you'll get lucky and maybe you can factor something and it'll simplify. Not here. All right, so if I look at the domain on f of x, I've already acknowledged there's no restrictions. G of x, I've already acknowledged no restrictions. But when I look at f divided by g, I am going to have a restriction. Because I did division, I can't let my denominator be 0. What's going to make this denominator equal 0? 3. So x cannot be 3. So then I have to, and that's that kind of extra restriction that happens on division. So I look at all 3 scenarios and any restrictions, that's my overall domain. Just for fun, going to put it in interval notation for you. All right, gave you another weird one. Radicals. All right, let's see what this is going to do. First thing I'm going to do is do the division on it. You take your f function, divide it by your g function. Okay, a lot more going on this one. Now, I'm not going to worry about rationalizing it. That part I'm not as worried about right now. So let's go ahead and leave it as is because I want to look at the domains on these. So the domain of f of x. I do have a restriction. I cannot let x be negative. So that means x has to be positive or 0. 0 is okay. So then I'm going to have 0 to infinity with a bracket on my 0. When I look at g of x, okay, this is a little trickier. Be careful here. I cannot let this be a negative number. So this right here has to be greater than or equal to 0. I'm going to add my x and then flip it around because I like it flipped around better. This is saying that x has to be smaller than 4. Smaller than 4 means this right here. Now, when you do the division, look at your domain right here. Look at that. It's really, remember, each individual, but you have to include any extra restrictions that happen right here. So because that's in the denominator, over here, when I put that bracket on that 4, that can't be a bracket anymore. Because if this was a 4, I'd end up with the square root of 0, which is 0, and then my denominator is 0. So I have to get rid of the bracket on that. So the f divided by g, well, but I guess I should, before I even talk about that, I should probably also talk about the numerator, because I can't let that be 0. I'm sorry, I can't let that be negative either. So let's kind of look at what's going on. So on this one, I'm going to kind of look at it as a number line and think about all the restrictions because I have to make my overall domain has to include any restrictions at all. So I'm going to look at if this was at 0 and this is over here at 4, my first restriction says that 4 has to be greater than or equal to 0. So I could have anything this way, but I cannot have anything down here. All right. The next one says that it can be anything smaller than 4. So it would be anything down that way, but it cannot be anything up this way. So the only thing that's going to work is where they both happen to work out, which is this overlap spot here. They both would be okay here, only one is okay on the ends. So then my domain has to be this space in here. But because of this additional restriction in the denominator, I can't do this closed dot. I can't do that bracket. I would have to look at that as an open dot. So my overall domain with everything included is going to be 0 to 4, bracket on the 0, parenthesis on the 4. Okay, told you it can get a little trickier than this. Everything works. All right, I'm going to move on. I know it's getting long and we're only halfway there, so stick with me. Here we go. Composite functions. The way that's worded, it says f is composed with g. And so that really what it means is that you are going to take your g function and you're going to plug it in. And I like this notation better, honestly. I take the g function and I put it in to the f function. So wherever there's an x, I'm going to replace it with a g of x. This is another notation. It's pretty common, so we got to use it as well. F of g of x. It means the same thing as this. So let's practice this a little bit. This means that I'm going to put -5 into the g function first. So putting -5 right here, squaring it, gets me a 25. So if g of -5 is 25, then I put 25 in place of it. And now I'm going to do f of 25. So you can see that if you put a 25 right here, minus 4, you're going to end up with 2 over 21. Okay. Let's do it the other way. What if it's g of f of -5? Now you're going to start off, and you kind of do parentheses inner to outer is how I think of this. You're going to do inside here first. So take -5 and put it into f. So -5 minus 4, that's a -9. So now I'm going to be doing g of 2 over -9. Not as pretty. All right, now you're going to take this -2/9 and you're going to put it into the g function. And -2/9 squared, that's actually pretty easy. You just square the numerator, square the denominator, and you're left with 4 over 81. All right, we can even get fancy and do g of -5. So that means plug -5 into your g function. Got it. Already did that. That's a 25. But then you're going to do g of 25. So now plug it back into itself. So now you're putting a 25 in there. Do you know what 25 squared is? Oops, I'm just going to do it up here. 625. Okay, now I love this example because it is a classic ACT question on the science part of the ACT, where you're evaluating graphs and you're taking information from one graph and having to move over to the other graph and use that. That is composite functions graphically. So you can see on the left, this shows a swimmer's speed with respect to the time. You can see that as the swimmer starts, they're increasing their speed. They're not really fast initially. They're getting faster and faster as they get going. But now we're starting to go, and I'm starting to get a little bit tired. And so how quickly they're improving and increasing that speed starts to level off a little bit. Okay. The second graph shows the swimmer's oxygen consumption as it compares, or how it relates to their speed. So here, if their speed is 0, they're not using much oxygen. I guess they're holding their breath. I don't know. Okay, but as soon as they start swimming, and the faster they start swimming, then their oxygen use starts to increase on that. Okay, let's look at what we got. It says, what are the speed and oxygen consumption after 20 seconds? Okay, so both of these, well, I take that back. After 20 seconds, the speed. So when you look here, after 20 seconds, boom, you just go up and say, okay, speed is 1.5 meters per second. But it also wants to know the oxygen consumption. And the problem with that is in this graph, it doesn't talk about time at all. So what we do is we have to take our answer from one and plug it into the other, because at 20 seconds, our speed is 1.5. So then we come over here and say, okay, our speed is 1.5. How much oxygen are we using then? And that doesn't look like it's quite at 10, so maybe at, let's say 9, I guess. So I would say the oxygen consumption is 9 liters per minute. Okay, so let's look at part B. How many seconds have elapsed if the swimmer's oxygen consumption is 20 liters per minute? Okay, so we're sort of working backwards there. I know that the oxygen consumption is 20 liters per minute. So I track that over to my graph, and I have to figure out what I think that would be. I feel like that's maybe like a 2.3, let's say. Okay, so my speed is 2.3, but that's not what they're asking. They're asking for the how many seconds. So I have to think, well, speed is 2.3. So over here, I got to look at 2.3 and come over and say, okay, I think that's going to happen at 40 seconds. So taking information from one, moving it over to the other. All right. The other thing we can do is kind of combining the two functions graphically. So doing addition, subtraction, maybe doing composite, whatever it might be. And so just to clarify, I'm going to call this first graph my f of x, and I'm going to call my second graph my g of x. All right, so they want you to find f of 3. So putting 3 into I guess that's not a very good number, is it? I was sitting there looking, f of 3, okay. I guess 3 is like right here, going up. Where does it hit? I don't know. I don't think it would quite be at 0.5 yet, so let's say it's at, I don't know, I'll go 0.25. How about that? We, of course, on graphs are going to be estimating some things. Okay, next one, it says find f of g of 1. So that means plug 1 into your g function. Right here, g function, 1. See what we get back. I get 5, and then I'm going to take 5 and plug it into the f function. So back over here, now I'm at 5, goes up. Oh, that hits nicely right there at 0.5. Okay, does this ring a bell from the science ACT? All right, here we go. F plus g of 2.5. So what that means is you're putting 2.5 into both functions and adding it together. All right. So 2.5 is right here. And I would get, in this function, I'd get a 25. But a 2.5 in this function is kind of weird and small. I wouldn't get a very big number. And so I would just get there's a 2.5 plus a 25, let's say. Actually, I feel like I should probably had said, since f of 3 was 0.25, maybe f of 2 is only like a 0.2. So 0.2 plus 25 is 25.2. Okay, just some ways of how you do those combination functions with graphs. All right, I am going to skip this problem, so it may or may not be in your notes. If it is, just put a big X through it. We're skipping that one. Last thing, we have to talk about the domain on these composite functions. It works differently. All right, so if I'm going to do like an f of g of x, kind of like this notation here, where you take the g function and you put it into the f function. Now, you actually have 3 things going on. You got your g function, and you got your f function, and you have your f of g of function. But here's the deal. I really don't care about each individual function, because you have to think of the order of how you do this. You take the g function. You're going to immediately plug it into the f function, so you never really see the f function by itself. But you do see the g function by itself. So I only have to look at the g function, and I have to look at the f of g function. I don't really care about the f function by itself. Is that okay for me to say don't care? I don't know. I'm going to do it. I'm going to say I don't care about the f by itself. So you only have to look at the g and then your resulting f of g composite function. Okay, so find the domain of the original and then the domain of the result. And we never use the domain of the f function in this case individually. It's never by itself. All right, here I thought I should try some different notation. I'm going to use that little circle thing now. But think of that as an f of g of x. So I'm going to take the g function first. So I have to look out for the g function. So when I look at the domain on my g function, it's just a nice quadratic. It has no restrictions. Now I can look at my f function and see that it's going to have a restriction, but I don't care about that restriction because I'll never use it individually. So you might note, I'll show you here in a second why I say it doesn't really matter, because I can see that I shouldn't let it be 4, but I really don't care. All right, so now I'm going to do the domain of the resulting function. So let's go find that resulting function, taking the g, and you're plugging it in for x right there. So this composite function would be 2 over x squared minus 4. All right, now I do need to look at the domain on this one, the resulting one. So I'm going to have to say x squared minus 4 cannot equal 0. That's what my restriction is. Now, you might be able to do this in your head, but you got to watch out because there's a couple ways you could do this. I just think of that as an equal sign and treat it the same way. You could factor it as a difference of squares, or you could add the 4 to the other side, and you got to square root both sides, but don't forget that when you square root both sides, you have to put your plus or minus on there. So x can't be 2 or negative 2. You would catch that if you had solved by factoring as well. Okay, so my domain on this, I'm just going to write it. These are just kind of my working up to my final answer, so I don't care about the notation on this. All right, so then for your overall domain, you have to look at the g, and you have to look at the result, and whatever restrictions, you combine all the restrictions together, so it looks like overall, my restriction, x cannot be 2 or negative 2. That's my overall restriction. Now, I'm going to go back to this just to kind of prove it to you that I don't really even care about the domain on the f function by itself, because when I go do the composite function right here, it's different. It's gone. So the fact that I wouldn't really want it to be a 4 doesn't matter, because when I put a 4 in the result, it's going to be a 16 minus 4. And I'm okay. It's totally fine. Okay, let's try this next one. G of f of x. I'm going the other direction now. I'm going to take the f function and I'm going to put it into the g function. So I'm going to take this and put it in right there, which means I'm going to have to take that thing right there and square it. Okay, so a 2 over x minus 4, and I'm squaring that. Okay, that's going to be a 4 over x minus 4 squared would be x squared, multiply the 2 and double it, square the last term. There we go. Now, I have to look at the domain for the f, because that was the first function that I grabbed, and then I went and plugged it in. So g changed immediately. So I don't care about g, but I care about that first function that I grab. So looking at that, it looks like I don't want x to be 4. And then I skip over the g, don't care, and I look at the resulting one. So my resulting one is right here, and it is a fraction, so I am going to have some restrictions, but you can look at where this came from. It came from an x minus 4, x minus 4, so I think that even here, I still have that same restriction, x can't be 4. So then combining all of the restrictions, x can't be 4. All right, we made it. Last slide. I made it harder though, so don't skip out on me. I've got a quadratic and I've got a square root. So got the square root's going to present problems for me. I know it is. So here we go. First thing I'm going to do is I'm going to take my g function and I'm going to plug it into my f function. Take my g, plug it into my f. That actually is going to work beautifully for me because I'm going to have an x and well, if I tug that, I guess I'm going to go ahead and just write it. Sorry, let me change that. I'm going to take the square root of 9 minus x squared, and I'm going to square it. And then I'm going to do minus 9. And then I clean it up, square root. Oh, I'm in luck here. Oh my, look at this. Look at this. How beautiful is this? That's simplified way down to that. So now when we're doing our domain, it is going to be crazy tempting to you to just look at your final result and say, oh, look, there's not a fraction, not a radical. It's just going to be an all real number situation. No, it's not, because you have to look at multiple domains. I would have never gotten to this stage without grabbing this right here first. So I have to look at the domain on this. And this is a little bit tricky. I don't want this to be negative. Okay, I'm going to show this over here on this side because I have to make sure that 9 minus x squared stays positive. So that's got to be greater than or equal to 0. Okay, so now there's a couple ways we can handle this. I'm going to try to bring it back to what you did in a previous chapter. I don't really like my x squared negative, so I'm going to take it to the other side, but I'm actually going to take both of them to the other side. It's a quadratic. I want it to equal 0. So I'm going to take the x squared to the other side. I'm going to subtract the 9, but since they're both on the other side, make sure you kind of switch that around so it looks like this. All right, then what we did is we factored this, x plus 3, x minus 3, and what you're finding here are your key points to put on a sign chart. So negative 3 and 3 are your key points, and you want to make sure that this stays less than 0. So we put in a test point. Let's put in a negative 4. When I put in a negative 4 here, this is going to be negative, and this is going to be a negative. And a negative times a negative is a positive. Now I'm going to pick a point in here, put 0 in. When I put 0 here, this is positive, but this is negative. And a positive times a negative is a negative. When I put a 4 in, positive, positive, positive times positive is positive. Now, I have to pay attention to what is it I want again? I want it to be less than or equal to 0. So that means I want this chunk in here. So this is all good to go. I can have any number between negative 3 and 3. So that is the domain of g of x, negative 3 to 3. I promised you it was going to get a little sneakier. Okay, now let's look at the domain of f of g of x. That's the resulting one. And I cleaned it up so much that it got down to this stage. And this stage, there are no restrictions. So it's negative infinity to infinity. But your overall domain is the combination of those two things, and that includes any restrictions at all, which means negative 3 to 3. All right. Last thing, could you do f of g of 2? Well, 2 does fall within my range of my domain, so yes, I can do that. If it didn't fall within that range, I couldn't do it. So I would plug 2 into the g function right here, and this is where you can see, like if I were to put a 10 that is not in this range and put a 10 and try to do 9 minus 100, it would immediately go imaginary. So that's why I'm only allowed to use these. When I plug 2 in, I get 9 minus 4. That's the square root of 5. And then I take the square root of 5 and I plug it in right here. The square root of 5 squared is 5 minus 9. So that would equal negative 4. All right, I'm finally done. Go do your homework.